All right, I think that's everything we need. Now, to turn it into something.
So, I have a confession. For the last, year or so, I've been hoarding every single shred of wasted filament from my 3D prints. And in this video, the first of a series, we're going to try to build a practical, affordable filament recycling setup that allows anyone to turn this into this. Let's get after it. So, first things first, a little bit of background. As we all know, while 3D printing has a ton of ecological and environmental benefits that I've discussed in previous videos, such as reducing the need for transportation, allowing us to fix things instead of replacing them, and much, much more, it does also generate a ton of waste. This can be something as simple as a failed print, all the way up to support structures, and even things as minuscule as purge lines. This has always just been considered part of the deal. But more recently, companies have started cropping up like Recycling Fabrique, who've proven that it can in fact be practical to recycle these failed prints into new filament that is not only usable, but also beautiful and functional. Unfortunately, it's still very early days for these types of companies. As the founder of Recycling Fabrique told me in a podcast interview, they're actually already inundated with more plastic than they can reasonably even sort, and they haven't even started accepting filament from outside of their home country of Germany. Meanwhile, I, like many of you, have been generating more plastic waste than ever before with my 3D printing. As this channel grows, I'm taking on bigger, more ambitious projects, I'm testing more unproven filaments and printers, and with the arrival of printers like the Bambu Lab A1 Mini, I've actually started doing much more multicolor printing, which, until I can get my hands on a Prusa XL here in Israel, inevitably means lots and lots of purge and therefore waste. Now, all this has me really wanting a solution to recycle my filament right here in the studio, especially since Printables recently added a section where you can actually list yourself as a recycling center and find other recycling centers, meaning that people can drop off their failed prints and someone like me will be able to recycle them into filament for future projects or just to give away to subscribers. The problem with all that is, up until now, recycling filament has been either prohibitively expensive or incredibly unreliable. Most commercial solutions for shredding old 3D prints cost thousands of dollars, and they don't even offer extrusion. For that, you either need a very sketchy homemade extrusion solution, which won't be very consistent, or a low-end commercial-grade solution, which, again, costs another thousands of dollars. And don't get me wrong, I really care about the environment, but it just doesn't make sense to spend something like $10,000 to recycle filament when you can literally buy like 500 kilos of new stuff for that same price. Which leads me to our project scope and challenges. Throughout this process, my goal is to build a complete filament recycling station which meets all of the following requirements. First, the entire setup needs to be small enough to be able to fit in a home or small office. None of these impractical solutions that really only make sense for YouTubers or commercial companies in the space. Now, that doesn't necessarily mean that it's going to be a desktop setup, but rather that I want it to be at least compact enough that if one of you out there wants to replicate my setup, you could easily find space for it in your garage or basement. Second, it needs to be able to reliably and durably produce a reasonable amount of filament for my use and perhaps other people in my community. Yes, I could probably do this build for half as much if I rejiggered a paper shredder or a blender and then drilled out a 3D printer nozzle to 1.75 millimeters. But from what I've seen of other content creators who've tried that route, that would not result in reliable, consistent enough results to actually produce usable filament for years to come. And I'd probably spend most of my time babysitting and tweaking the extrusion system to get the filament to be even half printable. Third, it needs to be reproducible by the average community member, i.e. you guys in the audience. Now, I'm sure that some of you out there could probably laser cut your own steel and design your own entire extrusion line at home, but I can't. And the majority of my audience probably can't either. And if we want this project to have any serious impact, it needs to be something that many of you can and will want to do on your own to serve your own communities. That will inevitably mean relying on readily available and well-documented designs and/or commercial products. With that said, my fourth criterion is that it needs to be reasonably affordable. Like, as affordable as possible given the other three constraints. My goal is to spend less than $1,500, and I'll be tracking my expenses for all of you throughout the build series. Now, I realize that this number is not what most people would consider affordable for their own personal use. But given our other constraints, it's still actually going to be a major challenge. What's more, I want to point out that one of the major impetuses for doing this project now was the addition of the filament recycling directory on printables. $1,500 is a lot of money, objectively, but if you think about it in filament terms, it's only 75 spools. And I figure if people are able to get these machines working reliably enough that they can then begin accepting other people's failed prints, then it actually shouldn't be hard at all to collect 75 kilos of filament over the course of, say, 2 or 3 years, which is a reasonable time horizon for recouping an investment. Honestly, I'm not sure what you would do with the filament if you're not able to print that much. I mean, perhaps you could sell it back to its original owners at a discount, or list it on your local Facebook marketplace, or use it yourself for an Etsy store. Honestly, we can cross that bridge when we get to it. For now, I'll just be really happy if we're able to intercept some filament from the landfill and redirect it back onto a usable filament spool. And while we're at it, I think it would be really cool if we had some kind of big, hairy, audacious goal as a result of the ripple effect from this project. For example, to save 10 tons of filament from landfills as a result of this video build series. So with our challenge laid out, let's go ahead and get started with the first component, and that's the shredder itself. As I mentioned before, many have tried and most have failed to repurpose things like paper shredders or commercial or consumer blenders and things like that. And from my research, if we really want to be able to produce consistent and usable filament with a reasonable tolerance, that begins all the way at the first step, shredding. So as I embarked on this project, I scoured the web for commercially available shredders, only to find that most readily available solutions were A, wildly expensive, B, hand-powered, or C, all of the above. Fortunately, I happened upon a website called Precious Plastic, which, as far as I understand it, is or was kind of like a not-for-profit collective of people in the Netherlands, notably a guy named Dave Hackens, who created and uploaded all kinds of open source designs for things like shredders, injection molding machines, extruders, and much more. Now, their ultimate goal seems to have been to empower people to actually create small businesses around plastic recycling. I say seems to have been in the past tense because I found that the founders do seem to have moved on to other projects. A lot of their website is no longer updated, with the latest release and update in about 2020, and their tutorials leave a lot to be desired. Fortunately, they did leave behind a thriving community as a legacy, including a Discord channel, as well as the Precious Plastics Bazaar, where people from all over the world are able to list machines or DIY kits for each of the different designs. And that's where we're gonna start. Now, to be clear, there are 100% free and open source DXF files available online, which you can download and either cut yourself or send to any local service like Send Cut Send or just a local laser shop. But if you do that, you will still need to self-source things like the drive shaft, the pulleys, and the hardware. I consider doing all of this, but I honestly have no idea what it would cost to get that done locally here in Israel. And with so many people currently in reserves due to the war, I figured it was just going to be a lot easier and cheaper to import the parts. Now, I looked into services like this video's sponsor, PCBWay, but it just wasn't economical to have them make only one kit. And they explained to me that things like this are going to be much more affordable with just the sheer quantity of steel you need to cut if you purchase from someone who is already producing it in bulk. With that in mind, I started surfing the Precious Plastic Bazaar, where you'll be able to find all different kinds of suppliers from all over the world. At the time when I looked, nobody was actually willing to ship to Israel, but I did reach out privately to a few producers, and I managed to convince one of them, PP Cappy Spain, to update their shipping policies. They also informed me that if I purchased 2 kits, the shipping would only increase by 50%. So it would actually be an opportunity to recoup some of my investment, assuming I'm able to sell the other kit locally. So with all that said, I ordered 2 of their slightly older version 2.1 kits in regular non-stainless steel, complete with the Evolution drive shaft, and they were kind enough to do the chamfered holes for me free of charge. Altogether, those 2 kits came out to 700 euros shipped, or $758.48. I then had to pay import duties and customs of $129.19. You may or may not have to pay these duties depending on where you are, and you should be able to get them back if you're like me because it's a business expense for what I do. But until I actually get them back, let's go ahead and keep track of all of that. Also, in case you're local here in Israel and you want to build your own filament shredder, I am currently trying to sell the second kit for 1,750 shekels or $485. So please ping me on Discord if you're interested. Assuming I'm successful in selling it, it'll bring my entire cost down for this part of the build to just $402 with customs duties, or $273.48 if I'm able to get the duties reimbursed. That's really, really good, and it puts us well ahead of the estimated prices for new material on the Precious Plastics website. But we aren't nearly done, because up next, we need to source the materials for the frame. Of course, picking up some simple steel bars at a local hardware store would have been simple enough. But considering that this project is all about recycling things destined for the landfill and cutting costs wherever possible, I decided to take a slightly different approach. You might not realize it, but because of the current real estate boom and the fact that our government has mandated that every single apartment needs to be renovated with a bomb shelter, wonder why, the city is currently littered with what I lovingly call free hardware stores. Now, these hardware stores have everything you could possibly want, from copper wires to steel bars, dowels, and even readily finished wooden planks for other projects. But most importantly for this project, with a little bit of elbow grease, I was able to pick up some pre-owned steel bars and strips with which to build my frame, all for the low price of free. Now, the keen-eyed and clean-handed of you may be staring in disbelief at your screens right now, thinking, hold on, is this guy seriously looting a building that's scheduled for demolition? To which I reply, no, I'm not looting. I'm part of a small volunteer organization that spends their weekends reclaiming and recycling raw materials that are otherwise destined for landfills. Please, hold your applause and your praise. I'm not a hero. I'm just an everyday concerned citizen. Now, while Tel Aviv's wonderful free hardware stores have so far been able to provide me with just about everything I needed to get us up to this point, sometimes there are things that you can't find in a dumpster. Things like CNC machined parts, metal 3D prints, sheet metal fabrication, or custom-made PCBs. But don't despair, because all those things, and honestly much more, can be had both quickly and affordably thanks to this video's sponsor, PCBWay. Thanks to their incredible scale, PCBWay is able to custom fabricate honestly anything, from 3D printed parts and injection molded parts all the way to custom PCBs, sheet metal fabrication, and more, in quantities small or large, cheaper and with better customer service than the local suppliers here in Israel, and probably where you live too. They even have a real-life engineer check over every single design you upload to ensure that there won't be any issues in manufacturing. Pretty cool. We'll actually be using PCBWay for a crucial part in the next video in the series, but until then, do make sure to check them out using the link in the description, which will get you a free sign-on bonus to use on your very first order. So thanks again to PCBWay, our longest-standing sponsor. All right, let's get back to work, shall we? With our shredder kit and frame procured, we now need a motor. Precious Plastic casually states that any old motor will do as long as it's sufficiently powerful.
It doesn't really matter how it looks or how big it is or the size. We only need to make sure it's slow and powerful.
As in 1.8 to 2.2 kilowatts powerful. But there are actually a number of things that you need to take into consideration. Things that I wish I'd known before. Keep in mind, I'm not an engineer and I have zero experience with industrial equipment like this. So I'm just repeating back what I've learned by consulting with more qualified people like fellow YouTuber Clow42. But if I get something wrong, please do let me know in the comments below. So first of all, industrial motors of this size can be single phase or triple phase power. And before you pick one up, you probably want to make sure that you have access to triple phase power wherever it is you want to place this. Otherwise, get another motor with single phase power. Next, you need to consider the RPM of the motor. Most of the industrial motors out there spin at a crazy fast RPM, like 1,915 in the case of the one I picked up. That is way too fast for our application, and in reality, we really want a low RPM between 30 and 70 with high torque. Now, the most obvious way to achieve this would be to gear down the motor, generally with a right angle worm gearbox, such as the one you see in the assembly video by Precious Plastic. The third thing that you need to take into consideration is the mounting style. You can generally find the same type of motor with 2 or even 3 different mounting styles. There are those that bolt on near the drive shaft, generally to the aforementioned gearbox. There are those that bolt onto the frame from the body of the motor, etc. Unfortunately, I didn't know any of this when I went searching for motors on Facebook Marketplace. And since the instructions clearly stated that
it doesn't really matter how it looks or how big it is or the size,
I picked up the first one that I found, which happened to be a brand new 2.2 kilowatt 90L motor for 600 shekels or $166. Now that's a steal of a deal, so I obviously jumped on it, but given my ignorance, it also happened to be 3-phase power, high RPM, and without the mounting brackets needed to mount the body to the frame. But this is what we've got, so we're going to need to make it work somehow. To that end, instead of trying to source a gearbox that perfectly meshes up to this motor and its mounting points, I instead consulted with Clow42 and my local electrician turned personal friend Mohammed, who both told me that my best bet was going to be a variable frequency drive converter, or VFD. As I understand it, and let's be honest, I don't, this is something like an electronic device that allows you to input electricity from the wall on one end and then outputs electricity on the other in such a way that it controls the motor speed and direction, all without the need of a physical gearbox. That's pretty insane to me, and I actually don't understand the actual physics of how we're going to get a motor that wants to spin at 1900 RPM and low torque to spin at 30 to 70 RPM and high torque. But trust the experts, right? In any case, I ordered both the VFD and an external controller with buttons on AliExpress because stuff like this is crazy expensive in Israel for a total of $76.32. That brings our current total to $645 with duties, assuming I'm able to sell the second kit, or $516 if I get the duties reimbursed. Either way, we are still way under budget according to Precious Plastic's build budget, and that makes me really happy. That VFD is going to take a couple of weeks to get here from China, so for now, let's get to work on the assembly of the parts that we do have. To begin, I assembled the actual shredder unit itself. Now, this isn't super complicated per se, but the instructional video provided is far from comprehensive, and there are different versions out there, so none of it shows exactly what goes where. Fortunately, PP Capi Spain did provide me with their own documentation and tutorial video, and while it was in Spanish, I still was able to figure out and get the thing assembled. Now, admittedly, this did require taking it apart and reassembling it a couple of times to correct my mistakes, because between my rusty Spanish and just not following instructions correctly, I did have a hard time getting clear answers on which knife goes where and in what order. From there, it was time to weld the thing together. Now, please don't get intimidated if you don't know how to weld. I don't either. In fact, I only recently picked up my first basic DC stick welder, as I talked about in a recent video on Maker Tools that I wish I'd picked up sooner. Now, these welds are not complicated or delicate in any way, but they still were not easy for me as a beginner. In fact, I'm pretty sure that I still need to go back and improve some of those welds later, especially considering that the side pieces had nothing holding them in place until you successfully tack them into place. So it was really tricky to kind of hold it and weld it at the same time. But eventually, through trial and error, I did get the thing to a point where it held together. Unfortunately, the ceramic tiles that I'd been using as a workbench paid the ultimate price in the process. Not to worry, a quick trip back to the free hardware store yielded some beautiful wooden planks.
The only problem with the free hardware stores, the price is great. They don't offer delivery.
And one side quest later, I had a nice, new, and slightly crooked work surface. The next thing I needed to assemble was the frame, and here I admit that I was pretty out of my depth. In order for this thing to work properly, the frame has to be strong, sturdy, level to the ground, and built in such a way that the shredder shaft aligns perfectly with the motor shaft. Now, this might be easy if you have the right motor version with the mounts on the bottom, but we don't. So I had to use my seriously inferior steelworking skills to cut and weld all different kinds of pieces to make this thing work. I actually started out by modeling the entire thing up in Onshape using some readily available models from GrabCAD for both the shredder and the motor, but those models weren't 100% exactly like mine, so I eventually just decided to bite the bullet and start cutting and welding in the hopes that I could kind of figure it out as I go along. Now, in case I haven't qualified enough, remember that I am not a skilled welder, and I encourage you to let me know, respectfully, all the things that I'm doing wrong in the comments below. How else will I learn? In any case, as you can imagine, building the frame took me quite some time. I've been practicing by doing some small repairs and welds around the studio for a couple of weeks now, but this was actually the first thing that I've ever built from scratch using steel. For this reason, I really took my time. I measured twice, I used machinist squares, and all that. It was slow going, especially because my welding technique was absolutely atrocious at the beginning and my electrode kept sticking to the workpiece. It honestly took me literally the entire workday, but at around 4 o'clock, I finally had a stable, sturdy, and decent looking frame to show for all my efforts. At which point I lifted the shredder on top to match it, only to realize that I had measured the wrong side and all my dimensions were wrong. This meant that I would need to cut apart every single weld that I'd done all day and basically start from scratch. Honestly, I really should have just built this thing out of 2x4s, and if you're following along at home, consider building yours out of wood instead. Anyways, I'm not one to be deterred, so I decided to bite yet another bullet and put in the work to redo the entire thing. At that point, however, it was almost time to go home and be with my kids, so I decided that done is better than perfect. I cut all my welds, discovering in the process how weak and crappy they actually were, and I just started hacking version 2 together quickly and with little regard for perfect measurements, 90-degree angles, symmetry, any of that jazz. I figured that I could always compensate for uneven legs by either shaving the plastic end caps that were already on the steel beams or 3D printing my own legs with an added millimeter here or there. Fortunately, this turned out to be a pretty okay strategy because once I did get the version 2 put together with the right dimensions, I realized that the cheapy fake hardwood here in my studio bows up near the walls, meaning that if the steel legs had been around the same length all around, the frame would actually lean forward. So while this thing is admittedly pretty crooked, rickety, and just all around ugly as hell, it is not going to matter all that much. Plus, I do plan to actually bolt this thing to the wall for added stability, so I'm not going to fret about it being perfectly even or rigid as long as the legs can hold the weight of the shredder and motor nicely, which they can. To finish off the frame, it was time to build a motor mount. And as you will once again remember, the motor that I bought on Facebook Marketplace does not have the right kind of mount for this application at all. This meant that I would need to create my own mounting solution on the frame itself, which I did by simply using pieces of scrap from the 2x2 steel bars. First, I welded cuttings on the inside of the frame, and then I welded additional cuttings on top of those, which left a little horizontal play to allow me to adjust the motor left and right to meet up with the shredder. Vertically though, I actually got very, very lucky because it seems like this will perfectly bring the motor drive shaft into alignment with the shredder's shaft on the vertical axis. But we'll have to see about all of that in the next video. So I think that's a good place for us to stop for this week, but let's talk about next steps. In the following videos in the series, we're going to deal with the wiring and electronics, attaching the motor to the shredder, building some sort of hopper to feed the plastic in, creating a lower shelf on the bottom to hold bins that'll actually collect the shredded plastic, and finally, firing it up and then dialing in our shredding so that we're getting consistent and reliable actual shreddings. And then we'll tackle the next challenge, which is going to be extruding those shreddings into actual usable filament. So if you want to follow along on this journey, please do make sure to subscribe and consider clicking the bell icon so you don't miss out on future videos, because I'll not only be documenting my progress, but I also really want to share what I learn along the way so that hopefully some of you can build a similar setup at home. And once it's all done, I'll be sure to not only share the final cost breakdown, but also keep you updated on how successful I've been in recuperating my investment by churning out usable filament for myself or for the local community here. It's guaranteed to be a fun and informative ride, so I hope you'll come along for it. And we're back for part 2 of my series where I try to build an affordable and repeatable system for turning all of this into this. The first video really took off, and I was thrilled to see that you guys care as much about this project and about the potential environmental impact of it as I do. By the way, if you haven't already seen the first video in the series, you can go ahead and click on it up here to open it in a new tab so my algorithmic overlords over at YouTube don't penalize me for low engagement. Anyways, since the last video, I've been hard at work, and I have a lot of hard-won lessons and updates to share. Some good, some bad, and some very bad. So let's start out with probably the biggest area of headaches thus far, which has been the framework and welding lessons. As soon as I hit publish on the last video, I got back to work on my welded frame, if you can even call it that. As mentioned in the last video, I needed to build up some kind of motor mount to adapt the motor that I have to my proposed setup, which did not include a gearbox with a flange. More on that later. As well as I needed to add some bars in the back to kind of space the whole thing away from the wall and compensate for the trim piece near the floor. This took quite a bit of time to get right, especially drilling into the steel, since I clearly did not have the right drill bits. But eventually, and with a little bit of help from a friend, we got there. While I was at it, I also took the time to add cross braces depth-wise on the legs and a simple shelf width-wise, both to stabilize things and to hold the bins under the shredder. However, as a lot of people pointed out in a bunch of super helpful comments, thank you by the way for all of those, I was doing a lot of things wrong. First of all, I was not properly cleaning and grinding down the surfaces, which was then resulting in frustration, inferior quality welds, and very poor strength. Some folks even went so far as to predict that my frame probably would fall apart the minute I turned the motor on, which, judging by the fact that one bump against the wall knocked off the spacer piece, and the fact that the motor slipped right out of the bolts when I lifted the entire thing up by the motor, yeah, they were probably right. What's more, I didn't know at the time that I needed to be wary of galvanized metals, because apparently, if this metal that I'm working on is galvanized, then I'm inhaling some seriously toxic fumes. I really appreciate you guys looking out for me in the comments, and I absolutely love that we are learning together and doing this project as a community. It is so cool to me. Now, another thing that many of you mentioned that I probably should do is do this whole project with a MIG welder. So at the time of recording this, I'm actually looking into getting one. Hint, hint, if any sponsors out there maybe want to work with me on the next video. At the outset, I thought that buying and using the cheapest kind of welder out there, one that you could easily get for like $79, is what would make this project more practical and repeatable for all of you at home. But in truth, from what many of you have now told me, it probably would actually be easier and more realistic for absolute beginners to use a MIG welder, even if it means that you'd probably end up renting it instead of buying it. Either way, I really hope that the welding component of all of this is not what's going to stop anyone who would otherwise attempt this project, because I'm still really enjoying learning how to weld, and I wish that I'd gotten into all of it sooner. So let me know in the comments if you'd like to see more projects that integrate welding. I'd love to do them. In any case, MIG welders versus stick welders, that's all a bit off topic, and the fact that I chose one over the other doesn't even matter, because from the looks of it, we're actually going to have to redo a huge part of the frame anyways. Why is that, you might ask? Well, because again, judging by the comments and private messages from a bunch of people far more qualified than me in this area, I am going to need to change the drivetrain setup. It seems like the whole vertical frequency drive thing isn't going to work out after all. As many of you in the comments helpfully pointed out to me, and as I kinda sorta suspected in the last video, lowering the speed of the motor electronically does not increase the torque. And as you'll see in just a moment, the resulting torque would be nowhere near what we need to shred even the thinnest of parts, not to mention very thick ones like the ones I use later on in this video for the extruder set. Basically, after reading through all of your comments, I came to the conclusion that I needed a gearbox, and that I'd bought the wrong motor, and that I probably had wasted money on the VFD as well. This might seem like it's not a big deal, so I wasted a few days and possibly a couple $100 here or there so that you don't have to. I mean, after all, the beauty of being a content creator is that the journey, the entertainment value, and most importantly, the lessons I'm able to learn and then pass along to all of you are all far more important than whether or not I get things right or wrong on the first try. And while all of that is true, I was pretty devastated in the hours after uploading the video, despite the video getting really great reception from all of you. At that point, I had spent literally weeks planning, designing, sourcing, welding, taking everything apart when I did the welding wrong, and then welding things back together again. I drove hours to go pick up the motor, and then I purchased all kinds of components for it. I even designed and ordered CNC couplers from PCBWay, only to find out that a fixed coupler was going to be a big no-no for this type of application. Basically, every aspect of my proposed setup and execution up until that point was all wrong. And in the end, all I had to show for it was some learning and a video. I'm not gonna lie to you guys, I was super bummed. And I'll get into how things miraculously turned around in just a second. After a couple of hours of stewing in frustration over wasting my time and money, I actually received a bunch of messages on our Discord server from all of you guys, which really lifted my spirits and provided a glimmer of hope for two different reasons. First of all, I was reminded of just how amazing of a community we've built around this channel, that people would actually reach out and offer to spend their time dropping by the studio and helping me improve my welding technique. And I just remembered that I wasn't alone in all of this. We are all doing this together as a community. But second, one local subscriber, a sort of mad scientist from Haifa named Daniel, actually reached out to let me know that he not only had the exact right kind of worm gear box for this project, as you can see here, but that he would be interested in trading it plus some cash for that second precious plastics kit that I was trying to sell. That's two birds with one stone, and I love it when the universe lines things up for you like that. So over the weekend, while I was actually already in Haifa to visit my in-laws, I met up with him both to pick up the gearbox and exchange it for the shredder, and get some tips on welding while I was at it. So together, we strategized on the best setup moving forward, whether I should trade him motors or use a belt drive, and eventually we decided on my existing triple phase motor and one of the gearboxes that he had lying around in his shop. Now, it wasn't easy, but after a lot, and I mean a lot of prying, we actually managed to free that gearbox from the original drive shaft that was already embedded in there. At which point, we traded. Now, to keep the accounting simple, I sold him the extra precious plastic shredder kit for 1,700 shekels or $463, and then I bought the gearbox from him for 500 shekels or $136. Now, I just need to order 2 more pieces to make this gearbox work with the motor that we already have. First, I need a sleeve to adapt the 20mm drive shaft of the shredder into the output of this worm gear. And second, I need an adapter flange to actually connect the motor with its massive 200mm 4-hole flange to this tiny 97mm 6-hole flange of the gearbox. Now, to get both of those things done, I whipped up Onshape and I began designing them from scratch. Yes, I am pretty sure that there are off-the-shelf solutions available for both of these things, but I spent about an hour online looking for them and I couldn't find someone who could get them to me easily and quickly. And plus, PCBWay is a long-standing sponsor and partner, and they've agreed to hook me up with some custom CNC parts for the next video in this series. Now, as to whether or not I should include those expenses of the CNC parts into the final cost breakdown, we'll see. Because in all truth, the big takeaway from this whole experience is that if you're doing this at home, you should buy a secondhand motor and gearbox combo together, which are already adapted to one another. Ideally, just check out your local junkyards for deals like Dave did in his own assembly videos, but make sure that you get the gearbox with it. That'll not only save you money over purchasing each of them separately like I did, but it'll also mean that you don't need to worry about designing or paying for adapters like I'm going to have to. Before the next video, I do hope to do some research and figure out how much a combo like that would cost one of you secondhand so that we could do the accounting as a cost to recreate calculation without all of my mistakes and unnecessary expenses along the way. So stay tuned for all of that. By the way, one thing that I think is really important and worth noting here about 3D printing, because this is a 3D printing channel, before I ordered the CNC parts, I did 3D print my own designs to test out the fitment using a Diamondback nozzle that US Synthetic provided and PETCF filament for both strength and dimensional accuracy. But I was actually blown away by just how far off my dimensions were. So Daniel, who has way more experience with machining and steel and gears and stuff like that than I do, let me know that the standard tolerance for these types of applications is 0.05 millimeters. So I designed and printed the parts with that tolerance, but they didn't fit, like not even close. And to give you an idea of just how much they didn't fit, the 7.95 millimeter key slot from my design actually came out as 8.5 millimeters. That's partly because of the pressure advance issues on the corners with PETCF, which wasn't calibrated for that printer. It's partly because of the 0.6 millimeter nozzle, and maybe even because of the texturing on the outside of the carbon fiber filament. But it was really interesting and eye-opening for me just to see how different the levels of accuracy are between the prototyping technology, 3D printing, and machining. Personally, I just sanded things down to the dimensions they were supposed to be so that I could at least test things out. But if any of you out there actually have any resources or suggestions on using 3D printing to get accurate enough samples to test out before something as precise as CNC machining, I'd really love if you share them in the comments below. I'm curious if next time I should design 2 different versions of the parts, one with 3D printing tolerances and one with CNC machining tolerances, or should I just make adaptations in the slicer when I test the prototypes, or what do I do there? Anyways, for the sake of science and for thoroughness, my electrician friend Mohammed and his electrician friend Roman and I all decided to run all the triple phase wiring that we were going to need and then rig up the VFD and the motor anyways, directly connecting them to the shredder using a 3D printed coupler, as I'd originally intended, just to see what would happen. And as predicted by those helpful folks in the comments section, we were able to get slow enough speeds, but the output wasn't nearly powerful enough to shred even the thinnest piece of a failed 3D print. Not to mention that the fan of the motor was moving way too slow to actually cool the motor. We then compared that setup to the strength of the output with the worm gear, and we were actually surprised to find that with the right gearing in place, we were now able to shred plastic even by hand turning the input of the gearbox. But when we went to actually test, as you can probably predict, my 3D printed fitment sample coupler just snapped right in half. So before we continue with the shredder build, we will have to order the CNC pieces from PCBWay and rework the frame to now fit the worm gear and mount that up. And then we're gonna have to raise the gearbox to match that height. So at the risk of kind of jumping around too much and making this video a bit hard to follow, let's switch gears, no pun intended, and see if we can work on another part of the build while we wait for those CNC parts to actually show up. After all, shredding the failed prints is only one part of this equation. We'll then need to find a way to actually extrude that regrind into usable filament. This is more challenging than you might think. You see, the majority of the solutions out there are both extremely expensive and designed for extruding plastic pellets, which are both round and consistent. In order to extrude regrind, then, we need a solution which takes into consideration the variances caused by shredding recycled plastic. And in order to come within our budget, which I'll remind you is $1,500 or less, we can't really rely on any commercially available, readily built extrusion solutions. We're gonna have to build it ourselves. Fortunately, the clouds aligned recently, and Stefan from CNC Kitchen introduced the world to the ArtMay 3D extruder project, which fits our requirements perfectly. In case you missed that video, the ArtMay 3D is an open source project created by a craftsman in Germany named David. In a lot of ways, the project reminds me of RepRap itself in that it's open source and relies on both 3D printed parts and off-the-shelf components. But the most notable thing about the project, for our purposes at least, is that David offers the kit in two different versions. One for extruding pellets and one for extruding regrind. The differences, as I understand them, lie predominantly in the extruder's screw dimensions, though there are certainly some other differences as well. Since we're primarily, though not exclusively, going to be extruding regrind, the ArtMay is a perfect fit for our project. Now, to be clear, the ArtMay isn't cheap. It cost me €669 or $726 of my own money, including shipping, and that was before an additional $91 in import duties that I'm hoping to get back. Tack on 1.5 kilos worth of printed parts, which, although Sovol was kind enough to send over some of their super high quality PLA for this build, will add another $30 or so to our list of expenses. That's a lot of money, I know. And because this kit is open source, I guess you could self-source some of these parts from China or design a much simpler setup based on it for less. But as I stated in the first video, one of my main criteria for this project is repeatability, i.e., you guys being able to do this successfully at home. By choosing a ready-made kit with solid documentation, actual customer service, and parts that are already guaranteed to work together, I'm dodging a whole host of headaches and potential failure points and getting a product that, at least according to Stefan's video, already works great. And I'd much rather risk going over budget a little bit, but ensuring our success, than ending up throwing this entire project into the trash with nothing to show for it. And after successfully assembling the ArtMay, I have to say that I'm really happy with that decision. First of all, the design of this system, as Stefan said, is quite ingenious, using things like an infrared sensor to judge tension, gravity to control the filament tolerances, and even a swinging arm to spool the filament back and forth on the roll. I could never design something like this myself, and it kind of blows my mind that there are people out there like David who actually can. Second, the documentation is out of this world. Like, it's so specific, it literally has a page explaining to you the difference between the different types of screws or how to do various steps that you're going to encounter later. And then for each step, you actually have a pre-step before it instructing you on exactly which hardware to pull out from which individually labeled box in which individually labeled bag. This is a level of detail that I've never seen before, even on Prusa or Voron build manuals. In fact, throughout the build, I kept thinking to myself that it felt a lot like building a Prusa printer. That feeling was exacerbated by the components themselves. Outside of the extrusion screw itself, which David actually machines by himself in Germany, the ArtMay system uses almost entirely readily available components like stepper motors, generic boards and screens, and aluminum profiles, which will be really, really great if you ever need to replace any components. Like assembling a Prusa kit, there's no need for things like soldering or heated inserts, but rather standard hardware is embedded into the prints wherever necessary. Yet another way that this kit is similar to a Prusa printer is in the quality and origin of the components. To be honest, I would not have thought twice if the kit had shipped with a fair amount of Chinese components in the box. After all, everything's made in China these days, right? But I was surprised and impressed to see that David has sourced a lot of the materials from Germany. When we spoke, he lamented that he wasn't able to find certain things like stepper motors and control boards locally because no one makes them in Europe anymore, but that still hasn't deterred him from using locally sourced, European-made parts wherever possible. And his attention to detail in that regard is really quite impressive. The CNC milled parts, made in Germany. The wiring, the screwdrivers, the extrusions, even the freaking silicone, lubricant, and superglue are all made in Germany. You can see why I've started calling this the Prusa of filament extruders. The comparison still holds true when it comes to the actual build experience. I actually had a huge feeling of deja vu from when I built my Prusa MK3S Plus. And that's not just because I printed some of the heat-resistant parts in Filament's Prusa Orange ABS. When you build the ArtMay, you're basically building a 3D printer complete with aluminum extrusion frame, heating element, extruder, cooling fans, and electronics. It's just that on the ArtMay, instead of an XY motion system, the stepper motors are used for feeding the filament back up and turning the spool to wind it. And of course, the stepper motor that would normally drive filament into the extruder is actually a stepper motor that's turning the screw to push the shreds into also an extruder. Overall, the build was very enjoyable, much like building a well-documented 3D printer. Like a Prusa machine, it took 7 or 8 hours, and everything was included in the kit except a power supply. I struggled to find an enclosed laptop-style power supply locally though, so I just managed to find one that looks like the one on your 3D printer for 124 shekels or $34.15. It was going to take a few more days for that power supply to arrive, and plus, we can't actually test out the ArtMay until we have some shredded plastic. So while I waited for all that stuff to arrive, I did want to make some progress on the other aspects of the project so that we could really hit the ground running once everything is fully assembled. In that vein, and with a feeling of success now finally under my belt, I turned my attention back to the shredder and set about designing and creating a hopper to mount on top of it. This is important because it would be both impractical and wildly dangerous to feed plastic directly into the jaws of the shredder. Now, I've seen these hoppers made out of steel, but since we already know how talented I am with the welder, I did decide to this time go with wood. I actually found a bunch of drawers from an old closet thrown in the street and waiting for the trash man. So I decided to take a bunch of those, and then I stripped off all the hardware, the rails, and all that stuff. And again, I really love that we're building a plastic recycler out of recycled parts that were on their way to the landfill. Then, because the angles were really a bit tricky to get right manually, and because I wanted the hopper to have the maximum amount of volume without protruding depth-wise into the wall, I decided to design the hopper in Onshape, which then allowed me to export the panels to DXF format and cut them out on my laser cutter. I actually thought about creating those kinds of leaves in the design that you see a lot on laser cutting to kind of interlock and join all the corners just right, but I didn't know how the angles were going to work on the sloping part. I really didn't want to spend any more time on it, so instead I resolved to just glue the faces to one another at 90 degrees, which would obviously be extremely weak, and then just design and 3D print a bunch of brackets at the appropriate angles, which once again I did in Soval PLA. The added benefit of this method is that if one of these panels breaks somehow, I can replace it without having to break all the other ones like I would if they were locked together with wood, glue, and joinery. I also designed and 3D printed a bottom bracket, which I then glued to another piece of wood for strength, and then drilled holes in all of it to join it to the shredder itself. And since I already had the laser hooked up, I decided to engrave my new motto onto the front face. If you've made it this far, I would really love if you let me know in the comments if this slogan made you chuckle. The finished result, honestly, I think looks pretty good, albeit a little bit crooked on the shredder. And it is actually really, really strong. I'm able to lift the shredder, which is extremely heavy, up by the hopper. I particularly like how it won't protrude from the wall in the corner of the room, and yet I still have a huge amount of volume inside. So hopefully I can put a ton of plastic in here without needing to feed or babysit the shredder too much. If necessary, I'll design some kind of plate that sits in there, maybe with a weight on top, to kind of push things into the hopper. We'll cross that bridge when we get there, because there is still a lot of work to be done before we can even get close to shredding some plastic in this thing. Namely, we need to actually sort out all of this plastic. Now, I had already separated out PLA and PETG, but because I was inspired by Recycling Fabric's ability to produce beautiful, rich colors instead of just grays, blacks, or browns, I wanted to separate out specific color groups, at least of the groups that I have enough waste of to justify it. Now, this was a really, really satisfying task. I love doing this kind of stuff. And when I was done, I was left with bins for black, white, blues, and oranges. I'm actually considering, as you can see, mixing in yellow and red scraps with all the orange to see if it will even out to orange. But judging from Stefan's results, I think that the Artme may not mix the filament shreddings up well enough, and I may just have to stick to only orange waste. Let me know in the comments if you'd like to see me experiment with adding reds and yellows though, to see if we can even it out to orange. Additionally, I got ready for production by reaching out to a local filament manufacturer, Plastics App, who has agreed to sell me small quantities of colored virgin PLA pellets if I need. Now, I don't anticipate having trouble extruding the regrind. That's kind of the point of the Artme, but it might be really helpful to be able to mix in some virgin material or just pure, cleanly colored material to improve both the quality and strength of my final product. But we can experiment with all that later. For now, let's talk about what's left to do, what I hope to accomplish in the next video, and the outstanding challenges. Obviously, the most important thing is going to be reconfiguring the frame and possibly re-welding it using all the helpful tips that folks have shared in the comments, both for strength and for the new configuration with the gearbox. Now, that's going to require shimming and moving the shredder around, but one way or another, my goal for the next video is to have the frame done, the motor and gearbox mounted and connected, and then all of that connected to the shredder. I'd also really like to organize the wiring, mount it to the frame, and get this external switch box thing working before I hit publish on the next video. From there, I'd really like the next video to mostly be about trial and error, both with the shredder and ideally with the extruder as well. I've heard quite a few people who tried before me say that when it comes to making filament, garbage in, garbage out. So I'm actually really concerned about that for two separate reasons. First of all, my shop is extremely dusty, and I have no idea how much of that dust I'm actually going to be able to get off of the filament and wasted 3D prints, or even how I'm going to go about doing it. Like, should I try and hit the prints with a leaf blower before I shred them? Should I wash the shreds in a mesh bag and let those dry out in the sun? Let me know in the comments below if you have any ideas. Now, the second reason I'm concerned is moisture. Filament, as you know, absorbs water, and a lot of this stuff has been sitting around in the Tel Avivian humidity for a year or more. In order to get good results, I need to dehydrate the shreds. I do have an old oven here, but I'm not sure how accurate the temperature is going to be, and I really don't want to melt my shreds, which is going to be a challenge given how small they're going to be. Alternatively, I have a lot of filament dryers, as you can see, but I'm worried about the shreds flying around in there or, once again, melting. So I may need to make some kind of metal box out of an old strainer or something for all of that. Again, please hit the comments if you have any ideas. And also, while you're down there, let me know. Do you think we should include the cost of whatever we use to dry the filament into the overall build cost? Or assume that it's like basic tools and assume that most people will already have that? Anyways, those are the goals for the next video. We still have a lot of work to get done, plus a final cost breakdown. So if you want to follow along, please make sure to hit the subscribe button and the bell icon, just so you don't miss the next video in the series. In this video, I'm going to share with you some quick updates on my affordable filament recycling project. You'll see a few steps forward, a few steps back, and you'll learn a few valuable lessons that, unfortunately, I've had to learn the hard way. So before we get into the updates, I will start by saying that this video is going to be a little bit different than the others in this series. At the end of the last video, I said that I wanted the next video, this one, to be all about testing, both on the shredding and on the extrusion sides of filament recycling. And unfortunately, this video isn't that. I've run up against some major setbacks, as you're about to see, and because I'm going to be visiting family abroad for a couple of weeks, I wanted to share some relatively quick updates for those of you who are eagerly following along. And first, I really wasn't sure just how interested all of you would be in me documenting all my screw-ups, but you actually made it very clear that you're interested in seeing where things went wrong so that you can hopefully learn from them. So sit back, relax, and prepare to learn how not to build a filament recycling setup. As soon as I hit publish on the last video, I received a message from our resident mad scientist and savior, Daniel, who gave me a piece of very bad news. I would need to rebuild the entire shredder. As it turns out, I did everything right except for one crucial detail. I'd put all the knives on backwards. So instead of actually pushing the material into the fixed knives and shredding it, it would have just pushed it up. Son of... It wasn't fun, but I spent the better part of an entire day trying to rebuild the shredder without completely disassembling it, only to realize that it was in fact much easier to just take the entire thing apart and rebuild it. I then spent the better part of another day getting it aligned so that it spun smoothly, not realizing at the time that the bearings provided with the kit are actually self-aligning, meaning that I wasted a ton of time on multiple occasions aligning bearings that just would align themselves. God. With all that done, all I had to do was wait patiently for the CNC'd parts to arrive so that I could start putting it all together. Now, because I'd made a lot of mistakes in measurement already along the way, I really didn't want to mess around and try to calculate where I should drill the holes or weld the mounting points until I actually had things assembled and in their final positions in my hands. In short, I lost about a week of work just due to waiting for the parts. Fortunately, the parts did arrive and they looked, felt, and fit perfect. In fact, now is probably a good time to mention that the only part of this project that has actually gone well has been ordering the CNC parts from this video's sponsor, which, as you probably guessed, is PCBWay. The parts arrived exactly as I designed them, and they even took the time to pre-oil the coupler, which needed it, but clean the oil off the flange, which didn't. Now, I was a little bit worried that I didn't select the extra tolerance option at checkout because I wanted to see just how precise their standard tolerance option would be, but the parts literally fit together exactly as I would have hoped, without any play, but also without too much friction so that I'd be able to remove them every time I needed to fix something, which, as you're going to see, is gonna happen a lot. In short, I'm super happy with my order from PCBWay. Like I said, it's probably the only part of this project that has gone without a hitch so far. So whether you need PCBs, CNC machining, metal 3D printing, injection molding, laser cutting, a whole bunch of other stuff, honestly anything, just make sure to check them out using the link in the description or visit jle.vi/PCBWay to get $5 off your first order. Anyways, with these CNC'd parts now on hand, I went about putting things together, but of course I didn't have the right hardware on hand to actually mount it to the frame. Now, I knew I should wait, I knew it, but after months of working on this project, I was really impatient and I just wanted to see it in action. So I decided to just turn it on for 1 second just to test that the motion was working. This ultimately led to one of the most triumphant moments of my adult life, followed immediately by one of the worst. The motor kicked into gear, turning everything as expected. But you probably know what happened next. Heck, even I knew that it was probably going to happen. The sheer power of the motor turned the entire shredder, which lifted off the frame. I'd honestly thought that I'd either be able to hold it down or catch it or cut the power in time, but fun fact, did you know that a VFD doesn't cut power immediately? Yeah, I didn't know that part. So basically, the motor fell on the ground, bending the shroud and shattering the cooling fan. Fortunately, repairing the motor wasn't that big of a deal. Another fun fact here, I literally had never thought about the origin of the phrase hammering it out until this moment, as I was hammering out the dents in the fan cowl. I also had to drill out a bunch of the fan shroud screws because they snapped clean in half when the motor fell on them. By the way, I will have to apologize here for the lack of B-roll showing a lot of this stuff, especially when we get to the much bigger oopsies later on in the video, because honestly, I just was not in the mood to record footage as I was putting out fires and grumbling through fixing all my screw-ups. Anyways, with the shroud somewhat back in shape, I cracked open Onshape and I designed my own version of the cooling fan, which I printed in ABS to prototype and then polycarbonate for the final version. Honestly, I just wish that all of my screw-ups throughout this process were as easy to fix as that one was. With that repaired, I headed to my local hardware store the very next day to buy a bunch of hardware so that I could start mounting everything onto the frame. I also went about measuring where I would need the mounting holes and then adding more steel extrusions at all the different points where I actually needed the frame to be thicker. I actually had run out of steel bars in the last video, but fortunately I squeezed in one more trip to the free hardware store on my street before they demolished the building, and I picked up a motherload of steel bars. Side note here, I was so focused on applying everything that you all have taught me about welding during this process that I actually didn't think to clamp the bars together properly. So instead of putting something flat on the top and the bottom to ensure that they were level with the existing frame, I clamped them like this, and it turns out that they were thus at a slight angle. So I had to spend an hour or more grinding the new mounting bars flat, which weakens them significantly. Lesson learned. I also learned that it is not a good idea to try to lift a precarious 50-kilo shredder and motor setup onto the frame by yourself, because I then managed to drop it once again, this time onto myself. But both of those lessons pale in comparison to the lesson I was about to learn. You see, with this new layout, the gearbox is a little bit lower than the input for the shredder. Now I knew this, and I also knew that I needed things to be exact, so I planned to take something that I knew would be flat and level, unlike my welding work. I took a piece of coated plywood used for cabinets, and I cut out a hole for the shredder. Then, to get things exact, I lined up the shredder with my eyeball, and then pushed different sizes of washers under the mounting holes until everything looked level and even. Then, given my experience with the whole thing flying away on me before, I bolted everything down extra tight onto the frame. I didn't realize it at the time, but this would turn out to be the nail in the coffin. But before I discovered that, I did have a few brief moments of victory. The shredder worked. It actually shredded plastic. Yes! The VFD controlled the speed, and I was able to shred about 1 kilo of plastic. You guys, I was in a state of absolute bliss. The only thing was the knives kept getting stuck on thick pieces, and the motor was heating up like a lot. Also, there seemed to be a little bit of rocking with the shredder kind of dancing back and forth. Plus, the plastic on one side of the shredder seemed to be melting. What the heck? Look, I'm going to spare you guys the gory details of diagnosing the issue, not only because I really don't want to talk about it, but also because I was once again in no mood to record B-roll footage. I'm sorry. Let's just say I spent the next 3 entire days doing everything I could to figure out what the heck the problem was. Was it the coupler? The gearbox? Did I fail to grind everything completely level on the frame? I took everything apart. I even took the whole shredder apart twice, just to see if maybe I had mounted the bearings wrong. Again, not realizing that they are self-aligning to protect from exactly this type of thing. In the process of disassembling it, I had to cut all of my welds that honestly were much stronger than any of us could have predicted. But of course, Murphy's Law, only on the parts that I would later have to disassemble. Irony at its finest. Ultimately, I threw in the towel and I begged my new BFF Daniel to take the train down from Haifa to come help me diagnose this issue. In exchange for burgers and Filament, Daniel spent the evening teaching me various tricks such as how to measure concentricity with a dial gauge and diagnosing the issues with me. I'm not going to beat around the bush here. We figured out the issue, and it's that my shaft is bent. Giggity. How could that be, you ask? I mean, it was straight when I installed it, and like me, you probably would assume that there is no way a 72-kilo weakling like me could bend 20 millimeters of mild steel. Could it be when I dropped the entire thing? No, that actually doesn't make sense. Well, after taking out the entire drive shaft for the I don't even know how manyth time, Daniel and I looked at the nature and location of the bend after where the grub screw was, and it all became clear. When I'd shimmed the shredder, I had spent a while testing different heights, not sure whether the space between the wood and the bottom of the shredder was 3 millimeters or 3.5 millimeters. And because there was a little bit of play as I was lifting it up by hand trying to find the perfect height, it was really difficult to figure out what that was. So I had bolted it down at 3 millimeters and then later decided to add another 0.5 millimeter spacer to shim it up higher. And that ultimately sealed my fate. You see, while I, alone, am nowhere near strong or heavy enough to bend the drive shaft, if you attach that drive shaft to 4 large bolts and then tighten them, it's basically the opposite of a car jack. So I had literally bent the drive shaft down using the bolts by approximately that 0.5 millimeter when I test fit it the first time. 0.5 millimeter doesn't sound like much, but it's a big deal when you're dealing with these types of forces. And that is where the friction is coming from. That's why the whole thing rocks, why the motor doesn't have enough power left over after lifting the shredder to shred thicker pieces of plastic. That's why it's overheating and why there's enough friction inside the shredder to melt some of the plastic. Daniel and I spent half an hour or so trying to somehow bend the shaft back into place, but ultimately we both agreed that we were just going to do much more harm than good, and that the only way out of this is either by going to a professional machine shop to fix it, or by ordering a new drive shaft entirely. Yeah, I'm pretty devastated. With that said, it's not all bad, and I do want to leave you on a high note, so let me tell you a little bit about the experiences I've had so far with extruding my own filament. After the last video, my power supply came in, and I got to work finishing the Artmate. Now, there were a bunch of things that I'd done wrong in the assembly, like wires that needed to be crossed and so on, but fortunately, it was all easy enough to fix. To test things out, I actually hand pelletized a bunch of filament with a flat cutter, and I was super excited to see my first extrusion ever come out. It was at that point that I decided to order all the parts for Teaching Tech's open source pelletizer, because I think that it'll be really useful to be able to pelletize last meters of filament rolls as a means of adding some uniformity and consistency to my otherwise random regrind. Now, I haven't gotten around to building that yet. Once I'd gotten the shredder fully tested, I did try extruding some of the raw regrind just to see what would happen. Artmate specifically recommends using only dry 4 to 4.5 millimeter or smaller granules, which is about half the size of the ones currently coming out of the precious plastic shredder with its 8 millimeter sieve. But here, once again, curiosity and frankly impatience got the best of me. To my surprise, the early results were actually pretty promising. I was able to extrude some filament, but as you might expect, it was pretty much impossible to get a consistent 1.75 millimeters diameter. I did try running my regrind through the shredder a second time, but it really didn't make all that much of a difference. I then tried 3D printing a hand sieve and hand sifting my regrind to only isolate the smaller granules, which I put into my cheapo toaster oven for a few hours just to test out drying. To my surprise, they did not melt so long as I kept the door cracked, so that actually might end up being a very good drying solution in the long run. Oh, and also, while I'm sharing positive updates, I did make one cool hopper upgrade while the shredder was out of commission. Now, in my early testing, I noticed that the shreds tend to fly everywhere throughout the shop, and it is super dangerous and messy, so as I'd kind of assumed before, a hinged lid is going to be necessary. But instead of wood, I took a suggestion from one of my YouTube members and actually made it out of clear acrylic, which I think will be really cool to let me watch and also film the shredding as it happens. All right, let's talk next steps. Most importantly, I need to either get the drive shaft fixed or order a new one altogether. Now, I was going to try and get that done, but then, as you maybe hear from the sirens, our government and the Ayatollahs decided to see who has bigger rockets, and now my kids are home from daycare, so that will probably not be able to happen this week. Regardless, once I figure that out, I am going to play around with extruding those 4 to 4.5 millimeter dried granules just to ensure that they are a good size. If so, I'm going to have to hand drill my own custom sieve for the shredder to replace that 8 millimeter one, which I've already removed. And that's probably going to mean finding a new free hardware store for the sheet metal. Now, just a reminder, it's going to be a little while before I'm able to share any updates about this project, because assuming World War III doesn't break out, I am going to be visiting family in the States for the next 2 weeks. But don't worry, because I am planning on taking my Positron V3 on vacation with me, and I will do my best to continue creating high quality content for all of you while I'm on the road. So there you have it, a quick, at least for a next layer video, update on where my filament recycling project stands. And hopefully you all have taken some very valuable lessons for your projects, especially if you want to try and recreate this project at home without all the speed bumps. It has been far from smooth sailing, but I do want to let you guys know that your comments, your encouragement, and just your interest in this project are really what's keeping me going. So thank you all so much for that. So what feels like a lifetime and a lot of wasted money ago, I set out on a pretty ambitious project here on the channel. I wanted to create a DIY at-home setup that could recycle failed 3D prints into brand new filament, and which was reproducible by all of you at home. It has been a very, very long journey with a lot of learning, expensive mistakes, and frustrations along the way, but I finally have something to show for it. Oh, yeah, right. These actually aren't that impressive by themselves, so I better actually explain. These 3D prints are made entirely from failed 3D prints, supports, and purge lines and things like that, which I ground up myself here with 0 additives, 0 virgin material, and as you can see, they're not half bad. So in this video, we're going to talk about everything it took to get here, what I learned along the way, and whether or not it makes sense for you to replicate my setup at home. Oh, and by the way, if you're new here, this channel is all about helping you get more out of this amazing hobby that is 3D printing, whether that's news, new product releases, tutorials, crazy projects. So if you love 3D printing and you want to learn more about it, don't forget to hit that subscribe button. So as a quick refresher, let me remind you where we left off last time, but of course, do feel free to use the chapters below if you just don't care. In the last video in the series, I was kind of at a low point when we left off. I had recently dropped the motor twice, I'd bent the drive shaft by tightening things down without perfectly aligning them, and while the setup was working, it was permanently damaged. Also, my granules were way too big to actually extrude them into usable filament. So while I don't want to waste any more of your time or relive any more of my trauma by recounting every gory detail of what it took to unscrew up my screw-ups and get back on track, here's the high-level summary.
I looked into getting the drive shaft straightened, but realized it would be cheaper to just order a new one, either from the bazaar or from PCB. I also tried to create my own 4.5mm sleeve out of scrap metal, but it proved too tedious and annoying without a drill press, so I ordered that from PCBWay as well. Meanwhile, I spent weeks chasing around industrial component suppliers who didn't want to sell parts to me, trying to find someone who had curved jaw couplers in stock in the diameters that I needed. Ordered only 2 out of the 3 that I ordered came. Eventually, I did find someone, but they told me that I needed to wait 2 months, spend hundreds and hundreds of dollars to get all the components shipped here to me in Israel, and finally, I had 3 components I needed to connect everything together.
Whew! Once the parts arrived, it was time to finish the build. By putting everything back together. By the way, a huge shout out to PCBWay for saving my butt with this replacement drive shaft, and for those of you who don't remember, they also saved my butt when I needed custom flanges, custom adapters, custom sleeves, all because I didn't plan ahead and buy a readily assembled gear motor. Despite their name, PCBWay is also, as you probably already know, a great source for CNC machined parts like these. Their prices are really, really reasonable, and their turnaround is fantastic. So a lot of times I genuinely find it much easier to just order stuff from them rather than trying to find a supplier anywhere else in the world. In fact, I honestly think that if I had just taken the CAD of the curved jaw couplers from Lovejoy's website and then uploaded them to PCBWay and then had them machined custom, it honestly would have come out to about the same price, except I could have skipped the 2-month waiting period. Anyways, with all the parts finally in hand, it was actually really quick and easy to reassemble things. I did have to drill some new mounting holes and move things around on the frame because the addition of the couplers actually changed the distance between the motor and the gear, but it is well worth it. Adding in the curved jaw couplers, as some of you tried to warn me in the comments of my first 2 videos, eliminates the need for perfect alignments, and it protects me from damaging the new drive shaft. And it also reduces vibrations and all kinds of other wonky stuff. I also needed to angle grind the old sieve off and replace it with the new 4.5mm one, but after having rebuilt and built and rebuilt this thing like 100 times over the last 6 months, none of that was really all that hard. Once the mechanical part of it was done, it was time to wire it up and fire it up. Here, once again, I called on the help of my electrician turned personal friend, Mohammed, who spent the better part of the day, thank you, Mohammed, helping me figure out how to wire things up and program the VFD in such a way that we could get the most possible power out of the motor given the electricity we have here,
Torque moves.
while simultaneously being able to use it in forward, backwards, and also have an emergency stop switch, because as we learned in the last video, when you have a motor this powerful, you really want an emergency stop, not a coast to stop. This meant getting a crash course in delta versus triangle wiring, VFD programming, and boy, let me tell you, I am very glad that I spent the better part of a decade before this teaching accelerated learning techniques, because between the welding, understanding industrial motion systems and couplers and all the different things and electrical components that I would need to understand just to make this project work, I've really put many of those techniques to good use. As you can see, the switches that I got were actually the wrong ones, and I'm still waiting on the right ones so that I can properly wire up the forward and backward switches. But I am pleased to report that at least on the electrical side, everything works thanks to the VFD and the temporary switch I had lying around. So I'm able to start, stop, and reverse the motor, and I can even use the dial to select the speed. With all that said, it's been far from smooth sailing actually getting this entire setup working to where I could actually print the filament. And I've spent over a month working through bugs and issues. Now, I won't bore you with all the gory details. I honestly don't want to relive them myself, but I do want to document some of it because, as I said, the idea behind this project is that someone should be able to use these videos as at least a helpful resource for building their own version of this build. So first, there have been all kinds of issues with the shredder. Namely, it has been heating up on one side, which is then causing the plastic to melt, and then that jams the machine entirely. Now, this severely limits how much plastic I can actually process in one session without waiting for it to cool down, which is a bummer because the duty cycle of the motor that I bought is such that I should be able to shred for literally hours and hours on end if I want to. Now, I have racked my brain trying to figure out what could possibly be causing this friction, but I'm actually pretty sure that I have figured it out. So basically, when I align the blades and set the pattern, I actually set them up in one continuous spiral, which is then causing all the material to be shuffled to one side of the shredder. Now, that wouldn't be so bad if the holes were larger, as the material would then fall through on its way to the other end of the shredder. But I've also, as you'll recall, swapped the sieve to a 4.5 millimeter one. So the material is being pushed and then repeatedly shredded over and over, which is causing friction. Friction causes heat. Heat melts the material, which then sticks to the blades and just creates this cycle. So whenever I actually get the time after recording this video, I'm going to need to disassemble the entire drive shaft portion of the shredder, realign the blades in a better pattern, and then put it all back together for like the 100th time. But I'm actually not sure what the best pattern of the blades is. Should I do it randomly, or maybe in a V that pulls the material into the middle of the shredder, or maybe a V that actually spreads it to the two opposite edges and divides the material up? If any of you actually know what the best way to do the blades is in this scenario, or you have any other ideas as to what might be actually causing this heat, please do drop me a comment below. The other major issue that I was having was just with the extruder. I actually spent literally hours and hours across multiple days trying to dial in my filament diameter to be just right at 1.75 millimeters, and I was always coming up short. I probably extruded like 100 or 150 meters of filament, all of which was garbage, and I was nowhere near close to the right diameter or even reliably extruding any diameter. Now again, I don't want to bore you with the details, but basically the nozzle filter was clogging repeatedly, and that's probably because of all the sawdust in my shop. Oops. Also, I may have spilled some of the gray regrind on the ground, and then not wanting to waste it, kind of just swept it back into the bin. Don't judge me. So yeah, despite the fact that I actually did thoroughly wash and dry all the filament before extruding, it was definitely clogging both on the extruder and on the printer. This led me to realize that A, any shreds that fall on the floor are as good as trash, and B, I definitely needed to change my procedure for actually washing the filament shreds. Eventually though, I was able to figure out a method that I think is working, and once I resolved that issue and I made a couple of small ease of use modifications to the ArtMay, well, miraculously, then all the very thorough and specific documentation that David provides suddenly was enough to create pretty good filament with very little practice or tweaking. Now, it's still not perfect because, like I said, there is an element of fine-tuning involved here, and experience definitely plays a factor, but we'll get into all of that in a minute. But now that we've documented the remainder of the build process and the hurdles for anyone looking to build one of these themselves, I do want to change gears, no pun intended, and walk you through the entire filament recycling process from start to finish so that you can see what it actually looks like to use this setup and how much work it takes to create filament. The first step of the process is sorting. Obviously, we need to meticulously sort our materials, ensuring that we don't get even a tiny bit of PETG or ABS or anything but PLA in with our PLA, and obviously vice versa. In fact, this is so important and the difficulty of perfectly cleaning all the equipment so significant that I actually personally decided somewhere along the line that it just wasn't worth the hassle, or in the case of ABS, sniffing the fumes, and I just decided that I only want to recycle PLA with my setup. Yes, you can clean out the shredder and the extruder, but since 90% of my waste is PLA anyways, and since ABS is really unhealthy to breathe in such large quantities, I actually feel pretty comfortable just not even recycling those other materials. In addition to sorting by material, you should also sort by color, unless you only want to make grayish brown filament. Personally, because I wanted to save on bins taking up so much space in my studio, I actually started by sorting into color groups. And I wanted to see if I could, say, make orange out of red and yellow. But if you want to have more granular, get it? Granular control over the colors you produce, it really is best to sort by colors very strictly. After all, you can easily store the regrind in small space-saving vacuum bags once you've shredded it, and you can always mix in different colors of regrind later. But once you've ground up purple with blue, it's in there for good, and with a setup this compact, you will definitely see the effect in your filament, whether you like it or not. Lastly, I should also mention that this is a good time to quality control your material. As you'll see later on in the video, this is one of those garbage in, garbage out things in life, so while you're sorting, do ensure that you cut away any areas that have any glue or remove any hardware, obviously, or get rid of any large debris that may have fallen into the heat. Then, make sure to note to keep your pile covered next time. Next, it's time to shred the filament. This is pretty self-explanatory. Place a bin under the shredder, turn it on, adjust your speed, and drop something in. Now you are going to need eye protection, and I do strongly recommend that you put an acrylic panel on top of the shredder so you can still see in even when you close the hopper for safety. I'm actually thinking about flipping the direction of my door panel so that it still protects me even while it's up, because shreds do fly when you open things. While the machine is shredding, it is definitely advisable to be nearby and monitor for jams or clogs. Depending on your motor, gear, and shredder version, you might be able to feed in more material into the hopper at once than I currently can, but the process can be a little bit slow going. I would just say take your time and enjoy the satisfying crunch of watching 3D prints get recycled. Up next is washing. Now this is a super important step, and one that if done haphazardly will cause a ton of the issues that I struggled with for weeks. See, I figured that the best way to wash the filament shreds would be with a mesh laundry bag to prevent messes or losing too much of the smaller regrind in the water. That was a mistake, namely because in my shop there is a lot of sawdust, and sawdust won't go through that mesh. That's why my next experiment after I'm done recording this is going to be actually washing the shreds in a bucket without any form of mesh to see just how much, if any, I lose. If that doesn't work, I am going to need to either print or manufacture some kind of different sieve or maybe a filter with holes that are small enough to let particles of sawdust and things like that out while keeping most of the filament shreds in. Because as you can see, the washing step is really, really important, at least if you're like me and you're storing things out in the open in an extremely dusty studio for over a year. Up next, it's time for drying. Obviously, you can't extrude sopping wet filament, but even if you didn't need to wash your filament shreds because somehow your raw material was perfectly dust-free, get off your high horse, you will need to remove the moisture from the inside of the filament itself. Failure to do this will result in bubbly, awful filament, just like it results in bubbly, awful prints. Unfortunately, most commercial dryers out there are too small or just not properly set up for doing this without having the shreds go in everywhere. So while I did experiment with the idea of upgrading a dryer to dry regrind, I realized that it's just cheaper and easier to find a used oven or toaster oven and just put the filament in there for 4 to 6 hours at 40 to 60 degree internal temperature. Remember, internal temperature doesn't necessarily mean the same as the temperature that the dial says. Remember to stir from time to time to ensure that the entire pile dries, but don't be an idiot like me and do that without wearing an oven mitt because you want to get a feel for how dry it is. Idiot. Finally, it's time to extrude the regrind into filament. This part takes a little bit of tweaking and tuning to get right to your exact setup, which will depend on the quality and size of your regrind. But once you get it dialed in, it is mostly an automated process thanks to the ArtMaze automatic puller. It will extrude the filament, manage the diameter by adjusting the puller speed, and even spool that filament onto the roll back and forth to get a reasonably spooled roll of filament. It's definitely not Prusa perfect spool. Like I said before, I did a couple of quality of life upgrades to the machine, which did help me personally get better results. But overall, as long as you don't have wet or dirty filament regrind, the ArtMaze should perform as expected. The manual here is definitely very thorough and very much your friend. And by the way, take it from me, if you're having major issues, not little dials and tweaks, the problem probably isn't how you built the ArtMaze or even your settings on the ArtMaze, probably the quality of the material going in. At least it was in my case. From there, we have filament that is ready to print. So how does it print? The biggest question on everyone's mind at this point is probably, how much did all this cost? And we'll get to that in a second. But the second biggest question is, how good is this filament actually? So far, honestly, pretty good. As I've mentioned a few times, I'm definitely still dialing things in both with the shredder and with the extruder. And I wanted to put out a video to update all of you before I take everything apart and start rebuilding it. So I actually don't have a ton of material that I've had time to extrude to play around with. But so far, I'm pretty pleased. The gray filament that I made earlier, well, that clogged a lot both on the extruder and on the printer. But as I mentioned, that was before I was taking all the precautions and cleaning processes as seriously as I should have been. The blue filament is still not perfect. As you can see, there are some small areas where there's either jamming or under extruding. But overall, I'm pretty happy with it, and I'm quite confident that with just a few more hours of tweaking and experience, I am going to be able to get this within normal tolerances of decent store-bought filament. As for the color, I actually really like the transitions, but I do wish that I'd done them more deliberately. Like I said before, I am going to be further sorting my piles of scrap into much more granular and specific colors rather than larger color groups. And then I'll be bagging those into individual vacuum bags so that I can choose between a very homogeneous color like blue or create my own gradient filament if I desire. I still am curious though, what would happen if I say mix red and yellow or blue and red. So if you too would like to see me do that in a future video or a YouTube short, let me know in the comments below and do make sure you're subscribed. And now let's get to the part that I've honestly been dreading for months. The part where I come clean and admit to you all what it costs. When I first set out on this journey, I knew nothing.
You know nothing, Jim. Levy.
I didn't know how to weld. I didn't know how industrial motors worked. I didn't know about worm gears or couplers or extrusion screws. So I foolishly thought that I would be able to complete this project on a budget of $1,500 USD. I did not. Throughout multiple rounds of revisions, redesigns, purchasing the incorrect parts, damaging the original parts, and generally just failing my way through this project, I watched the budget fly by me like a train in the night. But before I get to what it actually ended up costing, let me ask you, is the cost of this project really what's most important here? Isn't it really, at the end of the day, the skills we learned, the friends we made, and the fun we had? $2,700. It cost $2,700. Now, to be fair, it wouldn't cost you nearly as much to recreate this at home. Firstly, most of you don't live here in Israel, where shipping and customs are insanely high, and stuff like this is not readily available at a local junkyard. But more importantly, you can also learn from my very expensive mistakes and, say, buy a readily assembled used gear motor rather than piecing things together at a premium and then trying to machine expensive adapters to get it to work. You can skip the multiple iterations where I tried things that people in the YouTube comments literally warned me would never work, and you can save the headache of having to have parts remachined when you destroy them, because why would you listen to someone in the YouTube comments who clearly knows more than you do? I'm actually going to be uploading a spreadsheet to my Patreon supporters and YouTube members with links and notes, recommendations, and all different kinds of stuff that you could use to actually calculate and plan your own build. And I do plan on doing a much longer kind of brain dump video for members and patrons, where I will walk through every single component, the potential pitfalls, what you need to know when shopping or assembling, and really just give you all the information that I've accumulated that really doesn't fit in a YouTube video, and the algorithm certainly will not reward. But to give all of you the bottom line, because I do want to make this accessible to everybody and not just members, I would estimate that you would be able to build your own version of my setup without all the mistakes and mucking about for around $2,100. And that is assuming you live somewhere in the US where you won't pay customs for things like the shredder kit. So yeah, budget-wise, I failed. I mean, there are definitely places that you could significantly cut the costs, like getting rid of the motor and hand cranking. And I will detail all the different ways in the brain dump video that you could shave off cost without huge sacrifices. But for the average person, those cost-cutting measures are going to make things much more difficult long-term, and you're going to run a higher risk of damaging things, not having the performance you want. Really, everything in my bill of materials is already kind of the bare minimum you would want for comfortable use. Then again, if you figure that a commercial shredder alone costs roughly twice what my whole setup costs, and if you figure that complete ready-made 3D print to filament setups like Filament start at literally 10 times the cost of my project, I'll still say that this project was a pretty massive success. So that's what it costs to build one. The question now is, should you build one? Now, before we do a celebratory dance, let's remember the original big, hairy, audacious goal of this project. I didn't want to just create a setup that would recycle my own filament or filament of my community. I wanted to create a setup that was easy, affordable, repeatable, and reliable enough so that many of you at home would be able and inspired to recycle your filament and that of your local communities as well. So, have I done that? Is this a setup that you, watching at home, can and should build? Well, I think it really depends. Nope. I mean, probably not. Look, as much as I want to mark this project as a complete success and pat myself on the back for hopefully creating a ripple effect with all of you, I have to acknowledge the simple facts. A setup like this doesn't make sense for the average individual hobbyist or user. First, there's the cost. In order to earn your money back on this setup, you would need to recycle approximately 108 kilos of PLA at a comparable cost of $20 per kilo, or nearly 200 kilos if you consider that you can bulk purchase filament for like $11 a kilo these days. Yes, you could almost half the cost by hand cranking the shredder, but even then, you're talking about hand shredding like 50 or 60 kilos of 3D prints before you recoup your investment. Though, if you happen to have a motor or gear lying around collecting dust, or you happen to find a steal of a deal at your local junkyard, then all of a sudden the economics start making a lot more financial sense. But still, there's the time and energy to build this machine. Don't get me wrong, if you love doing projects like this and love challenging yourself and you've been looking for an excuse to learn how to weld, then yeah, this makes a lot of sense as a first project. And truthfully, I think that because you don't have to go it alone and figure everything out from scratch the way that I did, you probably could do this in like half the time, maybe even less. But it is still quite a bit of work if all you want to do is recycle your 3D prints and get back to printing. Personally, I love doing new projects like this and learning new skills, and I've always wanted to learn how to weld. So for me, this was mostly a good experience when I wasn't screwing things up or fixing my screw-ups. But finally, there's the glaringly obvious one. New filament is just too cheap. That's why even when big companies get the raw materials for free to recycle them, such as Recycling Fabrique does, it is still more expensive to process recycled materials into filament. With that said, money isn't everything here, and this is a classic sense of what economists call an externality. There is some significant value in saving plastic from the landfill, so it's not fair to compare prices dollar to dollar without taking some of that into consideration. It might sound silly, but to the more tree hugger-esque of us, the environmental impact of this is really what's appealing about it. I mean, personally, I'm gonna be completely honest with you guys. I kinda get as much free filament as I could ever want thanks to generous companies like Polymaker or Sliceworks. And yet, I still decided that I wanted to spend my own money, thousands of dollars of it, building this entire project because I really care about reducing my waste and the impact of my 3D printing. Then if you consider that I actually saved a ton of steel and wood from the landfills in the process of building this thing, I actually feel pretty good about the expenditure of time and money building this thing. And let's remember, this setup isn't just for me. One of the big draws of doing this was to be able to list myself, or list yourself if you build one, as a filament recycling center on sites like Printables, and then have others donate their waste for upcycling into new filament. So while 100 to 200 kilos of filament sounds like a lot, and it definitely is on a smaller, non-commercial setup like this one, over the next 5 to 10 years, I'm pretty sure that I should be able to recycle that much filament. And who knows, maybe I could sell it at a discount to the local community members to recoup my costs, or give it away as prizes to local subscribers. All in all, I guess I'd conclude that while this probably doesn't make sense for the average 3D printing enthusiast to have in their home, at least not the whole shredder part, maybe the extruder part, I can definitely recommend it as a solution for businesses or makerspaces, engineering schools, or any other situation where you're going to have a lot of waste or access to actually collect a lot of waste from other people. But hey, I actually really want to know in the comments below, what do you think? Would you spend as much as $2,100 to recreate this setup if you knew that people in your local community would send over their failed prints? Would you rather just build the extruder and make new filament but not recycle the old stuff? Would you bring your failed prints to someone if they built a setup like this near you? Or did I fail miserably and waste over $2,000 on a silly novelty project? Also, let me know, do you guys still want to see more videos where I experiment with things like mixing different colors, strength testing the recycled prints against new filament prints, and answer all of your questions? Or have you kind of lost interest in more videos in the series now that it is revealed to be so much over budget? Ladies and gentlemen, we did it. After nearly a year of work, thousands of dollars spent, and countless screw-ups and dead ends, I can now officially say that I am able to recycle my failed 3D prints, supports, and multicolor poops into usable, consistent filament. Filament that works on nearly all of my printers, even those with a 0.4mm nozzle. And not just prototyping filament either. Filament that is good enough to use for normal, everyday printing of functional parts. And in this video, I'm going to tell you how we got here, the hurdles I had to overcome, how I could have saved time and money, and what I learned, so that you too can decide if this is a path you want to go down. let's get after it. Now, technically, this is the 6th video in this series. I'll go ahead and link the playlist below if you want to come along for the entire journey or catch up, but I'll also do my best to catch you up as we go along or fill in those of you who haven't seen every single video. When we last left off, I was finally able to create reasonably consistent filament, albeit filament that clogged pretty frequently, and which had a kind of cool but unintentional transition effect to it. At the time, I thought that by simply improving the cleanliness of my regrind, I would soon be able to create even more consistent filament that didn't clog. I honestly had no idea what was waiting for me. The first thing I did was to make some improvements to the shredder. These included creating a funnel to allow only shredded plastic into the bin, isolating any wood chips or welding slag from my poorly constructed frame from falling into the bin at the same time. I also added a powerful CPAP fan to the top of the shredder to help expel heat and sufficiently shredded regrind from staying past its welcome. Technically, I already covered these upgrades in a video outside of the series, which was about designing 3D printed solutions for real problems, but I didn't do an actual video in this series about it. And I guess that's kind of a good thing because both those things largely ended up being dead ends. You see, one of the biggest issues I was having, besides of course contamination, was overheating, hence the fan. But over the course of months of testing, I came to realize that it wasn't going to be as simple as just expelling the heat with a fan. In reality, while a lot of the heat is generated by the friction of shredding material, a large portion of it is actually being generated by the shredder itself, which is still rubbing up against itself and creating metal shavings, and a ton of heat in the process. I'll cover how I'm dealing with those metal shavings in just a minute. For now, as far as the heat goes, I haven't been able to permanently and sufficiently solve it. I've taken apart the shredder more times than I can count. I've rearranged the blade pattern, I've moved blades further up the drive shaft, and none of these fixes have lasted more than a few days. But my hope is that eventually the shredder will kind of break itself in. It'll grind away all the offending material and maybe operate more smoothly. Another cause of heat was the sieve size. You may recall that this design, the Precious Plastics Shredder 2.1, comes with an 8mm sieve, and that was simply too big for the ArtMay extruder that I'm using. Previously, I'd ordered multiple replacement sieves from PCBWay, who, by the way, is the sponsor of this video, in both 4.5 and 5mm hole sizes, and I'm very glad I did. I started out with the 4.5mm one, and that was causing way too much material to build up in the shredder, which would then churn, trap in heat, and clog the shredder entirely. Fortunately, I was able to hand cut some steel plates and recreate the sieve using the 5mm mesh that they created for me, but I unfortunately found out that the steel I'd used for the side panels was not hard enough, and it completely bent when I tried to screw it into the actual shredder. So I'll be ordering replacement parts again from PCBWay, this time in the right steel. Actually, I was planning on making my own replacement parts to make another sieve now that I have a Carvera Air CNC here, but it turns out that it's really hard to find someone who will sell you a small amount of 3mm thick stainless steel sheet. Like, I can easily find someone who's willing to sell me a 2m by 2m sheet if I'm willing to pay a king's ransom for shipping. But what the hell am I supposed to do with that much stainless steel? I don't think I can even get it down the stairwell here. That's why for things like this, even if you literally already have a perfectly good CNC in your shop, it's often much easier and even cheaper if you consider the investment of purchasing such a huge amount of stainless steel to just order what you need from PCBWay. They can CNC machine or plasma cut or 3D print just about any material you need, from stainless steel to different kinds of plastics to resin, titanium, all for a great price and with quick turnaround. They also have engineers go over every single order to ensure that there won't be any issues during manufacturing. You can check them out using the link in the description and get $5 off your first order today. As you can see, I finally just gave up trying to find someone to sell me a small amount of 3mm stainless and ended up ordering the parts from PCBWay. Plus, I think I'm also going to experiment with a 2-stage shredding process where I shred the material down to 8mm chunks first, swap out the sieve, and then shred it down to the 5mm or 4.5mm chunks. But while I wait for those parts to arrive from PCBWay, I'm fortunate enough that even though the sieve is kind of dangling in there, for now, it works quite well. And you can see that I'm finally getting really nice uniform regrind. And as you'll see in a bit, that is a huge part of getting high quality filament. Another thing I've experimented with in order to get higher quality filament is virgin material. I found a local high performance polymer composition company, Plastics App, who's willing to sell me some of their virgin high performance PLA pellets in really, really small quantities. However, this combined with the fact that it isn't just plain Jane PLA meant that it was really expensive. After shipping and taxes, the latter of which I do get back as a business, it ended up costing me about $28.57 per kilo for these high performance PLA pellets, which is about 2 times as much as finished filament should cost. Nonetheless, I decided to go ahead and buy it just for experimentation purposes. I figured that if it makes a really big difference, I could later buy normal PLA in bulk, potentially from a different supplier for much cheaper. I ran some experiments with 15 to 20% virgin PLA, and the first runs were honestly disappointing. Pockmarked filament that wouldn't give me a consistent diameter. Something was still wrong with my regrind, and I wasn't sure what. It was at this point that I started really experimenting with how I was treating and processing the regrind. After all, David, the creator of the ArtMay Extruder, repeatedly points out in his guide that this really is one of those garbage in, garbage out type processes. And there were numerous ways in which my regrind could potentially be garbage. First, I added a stack of magnets into the ArtMay's agitator, which now spin around and capture any metal shavings or fragments that might be in the filament. And let me tell you, does it capture a lot. This modification has been so successful that I actually recommended it to David to add it to the product itself. Though I will say that even after increasing the melt filter in the ArtMay to 0.6 millimeters, I still am not able to actually use a filter when extruding on the ArtMay. Anytime I add a melt filter before the nozzle, it clogs up after just a few meters, and I can never get the filament diameter right when it's installed. Fortunately, as you will see in a second, that turns out to be a non-issue. Additionally, and perhaps more importantly, I changed the way that I was preparing the material for extrusion as well. Whereas in the past, I was washing it to try and get rid of any errant dust, I stopped doing that altogether, partly because the stuff that I had washed ended up molding over, which ruined kilos and kilos of perfectly good regrind. But what's more, I started to realize that there was no way that my filament was this contaminated. There was no way that all of these little pockmarks were just dust and contamination. But what else could it be? After all, I was drying my regrind in an oven at 60+ degrees Celsius for 6, sometimes 12 hours to try and get out all the moisture. And the pockmarks appeared whether or not I washed the regrind. It was at this point that I happened upon a video by my fellow YouTube creator, Igor from My Tech Fun, which would pretty much change my life. That might sound like an exaggeration, but seriously, 3D printing as a whole, especially filament recycling for 3D printing, has been so much more enjoyable and easier since I saw this video. In the video, Igor tests the feasibility of drying various types of filament in a microwave. I know, it sounds ghetto, dangerous, irresponsible, sus, but it works. Like, really, really works. A handful of rounds of 30 seconds on, 5 minutes off in a microwave, and you can literally feel the humidity coming off of the filament. Just look at this. On the left, we have filament that was dried in an oven 2 times for 6 to 8 hours each time. And on the right, we have filament that was dried in a microwave for a handful of rounds of 30 seconds. Can you say breakthrough? This method works so well that I've actually connected the microwave oven here in the studio to Home Assistant, and I created an automation that I call Drying Protocol. It does 5 cycles of 30 seconds on, 5 minutes off to completely dry the filament in under 30 minutes, without me needing to babysit it or worry about the microwave melting it or worry about the oven starting a fire in my studio. And just look at the results. Look at this gorgeous recycled filament. It was this one change, properly drying the filament, that made all the difference. I was now able to do long prints, like 6+ hour prints, of course, using a 0.8 millimeter nozzle with almost no issues. But occasionally, and particularly with my black filament regrind, I was still having some issues. Eventually, by examining the area at and before the clog, I realized that it wasn't clogs at all, but in fact, it was filament jams. Simply put, my filament was becoming too wide or bumpy at certain points, and that would get jammed in the extruder or hot end. But why? I stood on this problem for days, printing only on printers that had smart filament sensors and jam detection, until one day it hit me right in the nose, literally. I was grinding up some black PLA into a nice big bin to extrude into a new spool of filament for an upcoming project. I nonchalantly threw in a piece of a 3D print that I no longer needed, and about 10 seconds later, my heart sank. The room quickly filled with a pungent but all too familiar odor, ABS. I had just irreversibly contaminated something like 10 kilos of material. But worse than that, I instantly realized what had been causing those blobs in my previous attempts. Somewhere along the line, I had contaminated my material, probably with ABS. It's hard to overstate how demoralizing this was. I had spent the better part of a year, thousands of dollars, and hundreds of hours of my time building this rig, separating my materials, shredding filament, collecting all my regrind into bins. And now I had around 20 kilos in total of completely useless material that would end up in the landfill anyways. I was honestly devastated. What was I doing spending so much time on this project when I didn't even know if it was going to be successful in the end? I seriously considered giving up the entire project, tossing all of the material that I'd collected over the last 3 years straight into the bin and just moving on with my life. Fortunately for me, the universe, God, the flying spaghetti monster, or whoever saw how demoralized I was because he, she, it, they sent another challenge my way. A challenge which would get me back on the horse. So due to logistical issues during the holidays and the war here in Israel, my huge shipment of Polymaker filament, which I desperately needed in order to make progress on that upcoming project, well, it didn't show up. Month after month went by, and for some reason, bupkis. I burned through every last shred of black and white filament, both here and at home, and I was completely dry. And at this point, I needed to be able to print things normally, not just on a 0.8mm nozzle. Things got so bad that I was printing PLA support filament for non-critical parts. In a moment of desperation, I turned to the 3 or 4 imperfect spools of recycled filament that I had made before the fiasco, and I thought to myself, what do I have to lose? I loaded them into the IdeaMaker IR3 V2, which I only have a 0.4mm nozzle for, and I hit print. What happened next kind of shocked me. It just worked. I mean, sure, every 4 or 5 hours, the smart filament sensor would trigger due to a jam, and sure, you could literally see the flecks of dust and metal shavings in the prints, but it was printing, like, beautifully. No stringing, no under extrusion. It was just printing on a 0.4mm nozzle, and the parts were dimensionally accurate. Emboldened, I started printing with the black filament on some other printers, and to my surprise, those worked too. In many cases, the parts were actually indistinguishable from virgin PLA. I was back, baby! I decided to put aside all the contaminated material for another project, maybe an epoxy table or something like that, and get back on the horse. I printed nearly 3 kilos of parts for that upcoming video, all with minimal jams and almost no clogs. I had done it, and boy, what a journey. Now, that isn't to say that I'm home free. I still have a lot of areas that I can improve. Like I said, the shredder is still heating up, causing it to occasionally spit out a kneaded, melted together clump of filament that I then need to manually remove. And I'm still struggling somewhat with black material being bumpy, to the point where I'm not sure if the black filament is just maybe more hygroscopic than the white stuff, or if I still haven't managed to get out every last bit of ABS contamination from the shredder and the sieve. What's more, I still suffer from pretty frequent jams if I don't load the shredder very, very gradually. So as I mentioned before, I definitely do want to still experiment with a 2-stage shredding process when I get those parts from PCBWay. And lastly, I'd like to get to a point where I don't have literal metal shavings in all of my filament, either by wearing the shredder down or by coming up with some kind of permanent fix for the friction. So if you have any ideas, please do share them in the comments below. With all that said, we're pretty much there. At times, many times admittedly, it felt like we would never make it. Like this would become just another project that never makes it past the 80% mark. But I am so proud of the progress we have made. And I literally couldn't have done it without all of you guys, whether it's local subscribers who helped me fix my screw-ups, or the thousands of helpful comments and suggestions that you guys left to guide me along the way. This really does feel like a communal effort, so thank you guys. And as such, because the whole idea behind this was for me to walk so that this entire community could run, I want to now bring it back and highlight some of the lessons that I've learned, particularly since the last video. For the sake of convenience, in case anyone is coming back and using this part of the video as a reference in the future, I will stick to kind of bullet points for each lesson rather than burying them in the story part of the video that we just got through. Lesson number 1, be ruthless in material isolation and sorting. The first and definitely the most painful lesson that I've learned in the last few months is just to be absolutely ruthless in sorting your material. Obviously, if you go down this path, you care a lot about recycling and saving material from going to the landfill. So it hurts to throw out perfectly good parts. But in the end, it is so much better to throw out one part than an entire bin of shredded material due to contamination. If there's even a 1% chance that the part is ABS or PETG, take it from me and just throw it in the trash. If there might be glue or other contaminants on or inside the part, throw it out. It's just not worth it in the long run. Lesson number 2, shred into smaller bins. But of course, there will be mishaps, especially if you, like me, aspire to accept waste from other people. For this reason, I advise you to never shred into large batches. Shred into small bins and keep batches separate so that a contamination event like my ABS mishap doesn't result in you throwing away more than a kilo or 2 at worst. Number 3, forget about other kinds of contamination within reason. Earlier on in the process, I was really stressed about things like dust, dirt, and even sawdust contaminating my filament. So much so that I washed my filament shreds in water to get all of it out, only to cause even worse contamination in the form of mold. Obviously, you can't have large wood chips or sawdust in your regrind, but within reason, it's been my experience that dust and dirt aren't all that big of a deal. Sure, it would be nice to eliminate the metal shavings from my filament, but removing them after the fact with a magnet inside of the hopper has been working just fine. Number 4, ditch the melt filter. With that said, if you are working with slightly contaminated filament, you will likely need to remove the melt filter in your extruder altogether. Sure, this means that debris will slip through the nozzle and into your filament, but from my experience so far, you'll get far fewer clogs on the printer itself than you will the extruder, which uses the melt filter. So I would forgo the melt filter altogether. Number 5, choose the right 3D printer for recycled filament. With all that said, your recycled filament is definitely never going to be perfect. At least I certainly haven't found a way to make it so. For that reason, I would advise being choosy about which types of 3D printers you actually run the recycled filament on. For one, I would advise against running it on any printer that doesn't have a smart filament sensor capable of detecting clogs or jams. But those are cheap and readily available to add to your Clipper printers, and most of the higher end printers these days are coming with them standard, so that's not too big of a limiting factor. Additionally, while you might think that it's the nozzle size that is going to dictate whether or not you can print recycled filament, I actually found that some extruders are more forgiving than others when it comes to diameter variations of recycled filament. Printers which have 3D printed components at the extruder, such as a Prusa or a Voron machine, tend to be more forgiving, whereas something like a Bamboo Lab printer, which has a very, very tight tolerance on the all-metal entrance to the nozzle, will likely jam much more easily. Experiment with the different printers at your disposal, or consider building a new tool head using something like the Orbiter and 3D printed tool head designs if you're serious about printing recycled filament. Lesson number 6, build a filament pelletizer. No matter what you do, no matter which printer you try to use, you are inevitably going to end up creating a lot of unusable filament should you go down this path. For this reason, I do suggest that you build a filament pelletizer early on in your journey to help you reconstitute that useless filament back into useful regrind that you can actually extrude. You might think that you could just use the shredder that you built to regrind up that filament, but unfortunately, a shredder is ultimately going to let a lot of large and long strands of filament through the sieve. So really, the only way to reclaim that imperfect filament is to go with a pelletizer. I've been using this free and open source design by Michael Laws from Teaching Tech, though I am definitely still in the process of upgrading it to hopefully run by itself without the need for me standing there and holding a drill. Going forward, I would definitely consider some form of pelletizer to be a required part of this setup or ecosystem. And lesson number 7, which is shredder, sieve size, and heat dissipation. Again, as I mentioned before, I am definitely not home free when it comes to a reliable shredder setup, but so far, what's been working for me is having a 5mm hole grid in the sieve combined with a high-powered CPAP fan for cooling. I'm pretty confident that the heat buildup to one side is the result of improper alignment on my shredder drive shaft or the individual blades being pushed too far to one side. But quite frankly, I'm not taking it apart and rebuilding this damn thing a 6th time, so it will have to do this way. All in all, I do think that the precious plastic shredder, if modified accordingly, can work for this type of application. And I also do look forward to experimenting with a 2-stage shredding process. So let me know in the comments below if you'd like to see yet another video in the series once I've had time to do all of that. Anyways, those are the major lessons and takeaways that I have to share at this point. Add them to the long list of wrong turns, screw-ups, and costly mistakes that I made along the way, which are all covered in detail in videos 1 through 5. For now, I'm excited and energized to keep tuning, tweaking, and improving my filament recycling process. And before you say it, no, this probably isn't cost-effective either in time or money for the average hobbyist. And yes, it is cheaper and easier to just buy virgin material, but that was never the point. Over the next few years, it is my sincere hope to save hundreds or even thousands of kilos of material from the landfill, both by personally recycling them here or by inspiring others like you to pick up where I left off and build their own 3D print recycling projects. So let's keep the discussion and the momentum going, either in the comments below or on our Discord server, where we've set up an entire recycling channel just for stuff like that. Guys, thanks again for watching and supporting me through the ups and downs of this entire journey. It really has meant the world to me. That's all for this week, but I'll see all of you on the next layer.